What if you have lone pairs on your central atom? There are two kinds of geometry. There's electron geometry and molecular geometry. The electron geometry is the arrangement of the electron groups. The molecular geometry is the arrangement of the atoms. So when there are no lone pairs on the central atom, the electron geometry and the molecular geometry are exactly the same. But if we have lone pairs, let's look at ammonia. I'll draw the Lewis structure here real quick. So there's our Lewis structure. We look at the central atom and ask ourselves how many lone pairs, electron groups, how many electron groups? There's 3. Plus 1 is 4. Oh my goodness, it's going to be a day. 4 electron groups, 3 single bonds, and 1 lone pair. 4 groups. 4 groups get away from each other by making a tetrahedron, right? So in this tetrahedron, we have 3 single bonds with hydrogen, and then we have a lone pair. The lone pair is a pair of electrons. It's repulsive to the electrons in the single bonds. But what about the size of electrons compared to the size of atoms? Really, really small, right? So here's a lone pair. They're taking up space. They're repelling these single bonds. But if we were looking at this and we could see atoms, the electrons would be too small to see. So I like to think of this lone pair as an invisible balloon. It's there, it's pushing the other things closer together than they would like to be, but you can't see it. So if we make this invisible, what shape do we have? A trigonal pyramid. See, it's not flat like the trigonal planar, because that invisible lone pair was pushing these guys closer together than would be in a trigonal planar molecule. And so this is a trigonal pyramid. It's a very squatty pyramid. It's not very tall, but it is not flat. So 1 lone pair out of 4 groups will get you a trigonal pyramid. Pardon me?
So it's not compared to tetrahedral because you just got 2 lone electrons. They're not.
Yeah, so the electron geometry is tetrahedral because there are 4 groups. But the molecular geometry, where the atoms are, is a trigonal pyramid. So in my mind, I imagine putting 4 balloons together. Okay, that's going to be a tetrahedron. And one of them's invisible. And then I describe what's left. That's a trigonal pyramid. Did you have a question? Okay. The lone pairs are actually more repulsive than the bonding pairs. We saw an example with formaldehyde where the double bond took up more space than the single bond. The lone pairs actually take up even more space. They're more repulsive. So if we look at this bonding electron pair, it is confined between the 2 nuclei, and so it's going to have a shape roughly like this. A lone pair, though, is sort of attached to this nucleus, but it's going to be able to spread out more over here. And so this one is going to take up more space. So we would expect from an ideal tetrahedron a bond angle of 109.5. You should know that angle. A perfect tetrahedron is 109.5. But what actually happens with ammonia is because this lone pair is more repulsive, it takes up more space, these angles are 107 instead. So they're pushed a little closer together. So you should be able to predict for ammonia that these angles are less than 109.5. Okay? Any questions? What about 4 electron groups with 2 lone pairs? Let's look at the Lewis structure for water. So usually we draw water that way. If we're just looking at the Lewis structure, not thinking about things very well, we might predict that water has a linear structure, right? Because, well, hydrogen, oxygen, hydrogen, they'll just line up, right? But water is not linear, and we know this by experiment. So on this oxygen, the central atom, we have, again, 4 groups. 4 groups make an electron geometry of a tetrahedron, but we have 2 lone pairs. So 2 of these groups are basically invisible. If we think of the balloons, 2 of the balloons are invisible. So if I make that invisible, that one goes away, and this one goes away. What we're left with is what's called a bent shape. That's a fancy name, huh? It's bent. Some books call it angular. I like bent. It's short and to the point. So we get this bent geometry because we're thinking of these lone pairs as being invisible. I'm just going to put them back. Well, the lone pairs are more repulsive. They take up more space. And so ideal tetrahedral geometry, the angles here would all be 109.5. But here we have 2 lone pairs, and so these hydrogens are squeezed even closer together than in the ammonia, and it's 104.5 because of those lone pairs. So electron geometry is tetrahedral. That's based on the number of electron groups. The molecular geometry is bent. Any questions? 104.5. Yep. So here's relative repulsion of electron groups. The lone pairs are the most repulsive, lone pair to lone pair. A lone pair to a bonding pair is the next most, and bonding pairs with each other are the least repulsive. So we see in methane bond angles of 109.5 because we've got no lone pairs. Here we've got 1 lone pair, 107. Here we've got 2 lone pairs, 104.5. What if we had 3 lone pairs? We'd have a diatomic molecule, and so there can't be a bond angle, right? That was a trick question. The question is, what if we had 3 lone pairs? Well, then this guy would be gone, and it's just the oxygen and the hydrogen. There's no angle to talk about. No, it's a trick question. Okay, so let's look at 5 groups. If we have sulfur tetrafluoride, so sulfur tetrafluoride, we put the fluorines around, and then we put lone pairs around. And we end up needing to put a lone pair on the sulfur because that will give us formal charges of 0. We look at this Lewis structure, we see 4 bonds and a lone pair, 5 groups. 5 groups make that the bipyramidal or trigonal bipyramidal structure. But this bipyramid had 2 different angles, right? If we put the lone pair in the axial position, up and down, the angle between the lone pair and the bonding pairs would be 90 degrees. If we put it in the equatorial position, then it's going to have between this lone pair and these atoms is going to be 120 degrees. And between this one and that one is going to be 90. And so we can get an average lower or greater separation by putting it in the equatorial position. I think of this, where should I stick it? So this is like a little girl, and this is her tutu. right? So you've got the head and the feet, and then you've got the tutu around. So there's more room on the tutu, on her skirt, her ballerina skirt. And so this lone pair is going to go where there's more space. So we put this where there's more space, and then we think of it as being invisible. So the electron geometry is bipyramid, or trigonal bipyramid. But the molecular geometry, just looking at the atoms, thinking of the lone pair as being invisible, we get this structure. And that's called seesaw. Like, what? How is that a seesaw? Well, you got to tip it on its side. Right? And this can go down, or this goes down, this side comes up. So it's a seesaw. Can you see it? Well, we've got some model kits. I'll make some of these and you can play with them during lab. Yes?
But the one on the angles on the equator, how do you call it, the equator or whatever, shouldn't the two fluorines be closer than 120 degrees?
Yeah, these will be closer than 120, and these might even be a little closer than 90. I'm not positive on that because of this lone pair over here that's squishing the rest of them together. Any questions? Let's look at boron trifluoride. Here's the Lewis structure. 1, 2, 3, 4, 5 groups. 5 balloons makes this bipyramid. So we've got 2 lone pairs this time. The lone pairs go where there's more space. So they go on the tutu, on the equatorial positions around the middle, where the bond angles are 120, with some of the others, and they're 90 with the axial. So we put both of those there, and then we think of them as being invisible, and what we've got left is this shape. And if you turn that on its side, I really wish they'd draw these that way. If you turn that on its side, it looks like a T. So this is called T-shaped. Some of these names are really fancy, like bipyramidal and tetrahedral, and then some of them are just kind of dumb, like T-shaped and seesaw. Any questions? About 5 electron groups with 3 lone pairs. So here's xenon difluoride. There are 2 bonds and 5, where did I get 5? 2 bonds and 3 lone pairs, a total of 5 groups. So this is going to make a trigonal bipyramid structure. The lone pairs, again, are going to go in the equatorial positions where there's more space. And then we think of them as being invisible. And so what this looks like is the ballerina in her leotard wearing an invisible tutu. And so that's called linear. So you can have a linear molecule that has 5 electron groups if 3 of them are lone pairs. So the electron geometry is the shape that the electrons make, trigonal bipyramid. The molecular geometry is just looking at the actual atoms. And that's linear. Any questions?
Yes.
Mm-hmm.
I remember back in 3A that the shape of the molecule was determined based on the electronegativity difference between the core atom and the orbiting atom. Like fluorine is more electronegative than xenon.
The electronegativity will affect the polarity of the molecule,
Right.
but it doesn't directly impact the shape.
So it's the lone pair repulsion.
Yeah.
So
It's a repulsion of the electron groups that impacts the shape. But when we talk about the polarity of the molecule, then electronegativity is important.
So the lone pairs are the bullies.
Yeah, lone pairs are the bullies. They take up more space. They hog. It's like, I want the biggest seat, and you go sit in the squishy seat, right? Okay, 6 electron groups. bromine pentafluoride. Here's the Lewis structure. It has 5 bonds and 1 lone pair. 6 groups. 6 groups make this guy, the octahedral. Well, in the octahedral shape, all the bond angles are the same. So you can think of that lone pair as being in any of them, right? It could be in any of them. And then, so we have electron geometry that's octahedral. We make this guy invisible, and this is what we see. We're not really going to talk so much about the bond angles with these more complicated molecules. These would probably be squished up a little bit, but it's not that significant. So this is called a square pyramid. Do you see the pyramid in there? So we've got a square at the base coming up. It's hard to draw a square pyramid. Okay, a square tent with 1 point at the top, a square pyramid. That's an octahedron with one of the balloons being invisible. So in my structure here, if we think of this purple bottom at the purple balloon at the bottom being invisible. We don't want to pop it. If we popped it, then the bond angles would change and things would move around. It's there, but it's invisible. The rest of these balloons make a square pyramid. Okay? What if we have 2 lone pairs in those 6 groups? So here, xenon tetrafluoride, 4 single bonds and 2 lone pairs. So again, the electron geometry is octahedral because there's 6 groups. 6 groups makes the octahedral shape. So if we put 1 lone pair here, the other lone pair, being a space hog, a bully, very repulsive, is going to go on the other side. Lone pair repulsions are the largest, and so these guys are going to get away from each other. And then we make those invisible, and what we have left here is square planar. So in my model here, with the balloons, if the purple balloons are the lone pairs, the red balloons are making a square. 4 balloons by themselves won't do that. They'll make a tetrahedron, but the lone pair, the purple balloons, are forcing them to be flat. Yeah.
If you were to put the lone pairs next to each other and opposite of each other, would they not touch each other?
If you put this lone pair over here and had this fluorine atom up there, it's not going to be stable because you'll have this strain between the adjacent lone pairs. And so that's not going to be stable. It's just not going to be that way. Yeah.
I remember in the previous slide that you just did, you had to hold the invisible lone pairs next to each other. I mean, what case would that be?
Okay, why were they next to each other over here? So here they're next to each other. But in this geometry, these 3 are in this equatorial position. They're like the equator, and the bond angles here are 120. And so if we have 1 lone pair here, the other lone pair could be here. Okay, that's still 120. It could be up here. Now it's got a 90-degree angle with that one. Or it could be down here. Again, 90 degrees. And so they're going to be next to each other, but they're equatorial and they have a 120-degree separation. The thing is, in this structure, in this geometry, you can't be away from each other, really. It just doesn't work.
Yeah, drawing 3 in the equatorial plane.
So here's a table in your book. That's a lot of stuff, isn't it? Do you have to memorize that? I'm glad you asked. No. Sometimes in the book, I don't know if it's in this book, but they'll say, well, just memorize the table. What? I don't think that's necessary. I think what's really helpful is just to learn the steps, draw the Lewis structure, count the number of electron groups. Ask yourself, how would the balloons get away from each other? There's only 5 shapes, right? There's linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. So once you, in your mind, make this balloon shape, then look at the number of lone pairs on the central atom and make that many balloons invisible. The only thing you have to be a little worried about is with these guys, trigonal pyramid and octahedral, when you have more than one lone pair, you have to put them in the right place. Okay? They need to go where there's more space. Okay? Any questions? Yes?
How does molecular geometry work when you're dealing with more complex molecules like glucose?
Okay, so what happens when we don't just have one central atom? We can look at the molecular geometry around each of the atoms that's not terminal. Terminal meaning it's only attached to one other atom. So hydrogens are always terminal. And you can have other atoms be terminal as well. But like in an organic molecule such as glucose or heptane or something, you have a string of carbon atoms. You look at each of the individual carbon atoms and you see they have 4 single bonds, no lone pairs. So each of those is tetrahedral in shape. And then what makes it even more fun is that there's rotation around single bonds. And so it's kind of like a snake, and it can wiggle around. That's a good question. Summary of VSEPR theory. So the geometry of the molecule is determined by the number of electron pairs, not pairs, electron groups. Electron groups on the central atom. We don't care about the lone pairs that are on other atoms. We figure out the number of electron groups by looking at the Lewis structure. You have to be able to draw a Lewis structure. These are the groups. They each count as one group. A lone pair, a single bond, a double bond, a triple bond, or a single electron in a free radical. That would be an unpaired electron. Geometry is determined by the repulsions between the groups. Bond angles can vary because multiple bonds are bulkier than single bonds, and lone pairs are more repulsive than bonding pairs. Yes?
You had hydrogen not connect to the central atom. Would you count that as one?
You only look at the electron groups that are connected to the central atom. If you have atoms like Max was talking about with more atoms, then you really have to look at the geometry around each of them. And so then you can't just give one name to the whole molecule, but you can say this is the electron geometry around this atom and this atom and this atom.
It's a monster.
It's a monster, yeah, and you can draw them to make them look like dogs and all kinds of stuff.